Imagine a world where AI helps diagnose diseases, writes patients' notes, and even recommends treatments. Well, that world isn't the future. It's happening right now. Hey everyone, I'm Harris, a medical physicist in the UK National Health Service and CEO of Newton's Tree. In this video, we'll explore what exactly is data-driven technology, the four main types of machine learning, and how these methods apply to healthcare, including the strengths and weaknesses of each type. So let's get started. Let's walk through a real-world example to understand what counts as data-driven technology and what doesn't. Imagine a patient using an automated insulin pump. This device includes a continuous glucose monitor that tracks blood sugar levels in real time and sends that information to an insulin pump. If the patient's blood sugar goes too high, the pump injects insulin to bring it back down. Now, according to the American Diabetes Association, a normal blood sugar level is up to 100 milligrams per deciliter when fasting and should stay below 200 after meals. So a basic insulin pump might theoretically be set up to do the following. If blood sugar rises above 200, it injects 1 unit of insulin. Here's the key question: is that data-driven learning? Well, if the pump simply follows a pre-programmed rule, injecting insulin anytime it sees a number over 200, that's not data-driven. That's a rules-based system. Someone hard-coded that decision logic. It doesn't learn and it doesn't adapt. It just executes a fixed instruction no matter who the patient is or what else is going on in their body. But what if the system starts learning from past data? Say it has access to millions of patients' medical history, how their blood sugar responds to previous insulin doses. Then it starts making predictions. Based on what I've seen, as this person's blood glucose is over 200, I'm going to inject 1 unit of insulin to bring it back to normal. In this case, the model is learning from data. It's not following fixed rules defined by a professional body like the American Diabetes Association. It's defining it based on patterns it's discovered in the records of millions of patients. That is what we mean by data-driven learning. So when we talk about AI in healthcare, it's not just about automation alone. It's about systems that derive their logic by learning from data. And that distinction is what separates traditional software from modern medical AI. Now let's look at the different ways data-driven technology learns. There are 4 main types of machine learning: supervised learning, unsupervised learning, reinforcement learning, and then other methods like semi-supervised, transfer learning, and active learning. Supervised learning is perhaps the most common type of machine learning. Here, the model learns from labeled data, which are examples where we already know the correct answer. In practice, supervised learning is used for 2 main tasks: classification, where the software is predicting a discrete outcome, like identifying if a mammogram is suspicious of breast cancer. And then there's regression, where the software is predicting a continuous outcome, like predicting a patient's blood glucose levels based on what they've eaten that day. These models learn by analyzing thousands of annotated images where a human expert has already labeled the data with the correct answer. But here's the catch: these models can struggle when they see something new. For example, if they receive a medical scan that looks different from what the software saw during training, say it comes from a different hospital, or the scan was captured by a different scanner, the system can misclassify what it's seeing. It also has other weaknesses. Supervised models are prone to bias, especially if the training data isn't diverse itself. They often face generalizability issues, meaning they may not perform well outside of their original context. And finally, there are often interpretability challenges. It's not always clear how the models arrived at a decision, which can be a serious issue in clinical settings. Unsupervised learning works differently. Unlike supervised learning, it doesn't rely on labeled data. Instead, it dives into large data sets to uncover patterns and relationships that we might not even know exist. Some key techniques include clustering, i.e. grouping similar data points together, like identifying different patient subtypes, or anomaly detection, flagging unusual patterns that could signal rare diseases or errors. And finally, generative models, which can learn the structure of data and then create new content. Think of it like predicting the next word in a sentence based on previous ones. In healthcare, one exciting use case is AI-powered ambient scribes. These systems listen in on physician-patient conversations and use generative models to summarize the dialogue without needing any predefined labels. That's unsupervised learning in action. While these models often struggle with interpretability, making them feel like a bit of a black box, they tend to generalize better than supervised models because they aren't tied to specific labels or narrow data sets. On the other hand, one of the major risks of AI scribes is that they exhibit a phenomenon known as hallucination, which is when the algorithm generates text that is plausible but either factually incorrect or incoherent. Reinforcement learning takes its cues from game theory and trial and error learning. Instead of learning from a fixed data set, the model interacts with an environment, making decisions and receiving rewards or penalties based on how well it performs. Think of it like training a dog. Every good action gets a treat, and every mistake gets a no. Over time, the model learns which actions lead to the best outcomes. In healthcare, one application is optimizing treatment plans for patients. For example, reinforcement learning could be used to tailor diabetes management strategies, adjusting medication, diet, and even lifestyle recommendations over time to find the most effective plan for each individual patient. Remember the example from the beginning of the video? That's exactly the kind of dynamic, decision-based problem reinforcement learning is really built for. But here's the downside. Reinforcement learning is highly unstable. It's also difficult to interpret, meaning we don't often know why it's made a certain choice. And it's prone to unexpected failures, especially when it encounters unfamiliar scenarios or edge cases. For these reasons, it's rarely found in a medical setting. Other methods are seen even less commonly in healthcare and don't fit neatly into one category. These include semi-supervised learning, which combines a small amount of labeled data with a large amount of unlabeled data. It's useful when labeling is expensive or time-consuming. And then there's transfer learning. Here, a model trained in one domain, say general medical imaging, is adapted to perform well in a more specific one, like detecting a rare disease. This saves time and resources by reusing existing knowledge. And then there's active learning method, which lets the AI ask humans for clarification when it encounters uncertain or ambiguous cases, a bit like a medical student raising their hand in class. Lifetime learning or continual learning models evolve over time, continuously integrating new data to stay up to date with the latest clinical knowledge. While these methods are used less frequently, they offer exciting possibilities, especially when applied to complex, real-world healthcare challenges that don't follow a fixed structure. Machine learning systems, especially deep learning, are powerful but also very sensitive and brittle, which makes them more unstable than traditional software. Unlike a rules-based system, these models can have unpredictable failure modes. This can create hazardous situations when used in healthcare, where small errors can have a big impact. One issue is unstable data dependencies. AI systems rely on data that can change over time. For example, new medical guidelines or updated clinical practices can make older training data less reliable. And then there are feedback loops. Where AI starts influencing clinical decisions, it can subtly change how clinicians behave. Over time, this can create new biases, both in the data and in the way care is delivered. But we'll cover clinical risks in more depth in another video. But for now, just remember, AI isn't magic. It's data-driven technology that relies on patterns in the data it has seen. And when that data is flawed, so is the AI. To summarize, today we covered how AI learns from data, not from hard-coded rules. We looked at the four main types of machine learning: supervised, unsupervised, reinforcement learning, and other hybrid methods, and broke down how each one applies to real-world healthcare scenarios. We also talked about the risks that come with using AI in medicine, from unpredicted failure modes to bias and generalizability issues. AI isn't here to replace physicians, it's here to support them. But to use it safely, we must understand its limitations. If you found this helpful, check out our other episodes for more deep dives into AI in healthcare. We've got plenty more coming on clinical risks, real-world deployments, and what it takes to make AI work in healthcare. Go ahead and like, subscribe, and share this video with a colleague if it sparks something useful for you. And if there's a topic you want us to explore next, drop it in the comments. We read every one. Thanks for watching, and I'll see you next time.